Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. It's been called the granddaddy of all quantum weirdness. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
QuantumLaserPointers.com.
Okay, so in this video we're looking at the dispersion of white light, and this follows on top of what I said in the previous video, that white light actually consists of all of the colors viewed at the same time, or at least 3 of the color wavelengths that is being perceived at the same time. But if we disperse white light, in other words break it up into the different color spectrums or the different wavelengths, then we actually perceive a rainbow of colors as illustrated here in this picture. Okay, so what I'm going to do is just explain to you why is light doing this. Why, when I shine light at an angle into a triangular prism, does it break up into these different wavelengths, and when it comes out it breaks up or it disperses even more, and eventually to show the color spectrum when it is shone on a canvas or on some sort of light screen. Okay, so why does that happen? Well, the one thing that you need to understand is that when light travels in a vacuum, okay, so when light travels in a vacuum, then the speed of light is given by the constant c is equal to 3 times 10 to the power of 8, and we've already mentioned that that's meters per second. However, when it is traveling through a medium, when it travels through a medium, in other words going through air or water, or in this case a glass prism, then there is what is called the index of refraction. Okay, the index of refraction. Okay, and the index of refraction is given by the formula n is equal to c divided by v. So what is this all about? Well, don't worry about it. It's not that important. All that you need to know is that velocity in the medium is less than the speed of light. So the speed of light is actually the very fastest possible speed in physics. You can't go faster than the speed of light. So when light passes through a medium, it goes at a lower velocity, and if we take the speed of light divided by the velocity of that wave in that medium, we get what is called the index of refraction. In other words, can almost be considered as a ratio by how much the speed of light is being reduced. Okay, in a sense you can look at it like that. So that's the one thing that you need to understand. And the denser the medium, okay, so the denser the medium, so when density increases, the index of refraction increases. In other words, the velocity decreases. The velocity decreases. Okay, so why does this influence the refraction of light? Okay, so when light bends in a different medium, it's called refraction. Okay, and it bends towards the normal of the surface. Okay, so why is this true? Why does light refract? In other words, why does, first of all, why do the frequencies bend? And second of all, why do the higher frequencies, okay, the shorter wavelengths, bend more than the larger wavelengths? Okay, well, in order to understand that, I'm going to use a comparison, and I want you to imagine that we have a vehicle traveling in this direction. So it's traveling at that direction, and it is about to hit a stream of very shallow water, and it's traveling at quite a high speed. So here's just from the top looking at two tires, two of the wheels of this vehicle. That's now two of the wheels. Okay, it is going to hit this shallow stream at an angle, which means that this bottom wheel, you can see, is closer than this top wheel, and obviously they're traveling at the same velocity. So that means that the bottom wheel, or the one that's here at the bottom of the picture, is going to reach the shallow water sooner. Now if this was, let's say, a tarry surface, then it's going to have a higher velocity on the tar than it has on the surface. So once it reaches the water surface, so once it reaches the water surface, and the lower tire is going to reach that first, it's going to start slowing down while the tire at the top, or the wheel at the top, is still going at the higher velocity. So if you have something going at a higher velocity than something else, and they are connected like this, okay, you're going to have that the outside goes faster than the inside, so it's going to turn. Okay, I hope you know that, or that makes sense to you. So what happens is that by the time that the second tire, so the first, well, let me draw that. Okay, the first tire has now entered. Okay, here's the picture after it's entered a little bit. Okay, and you can see only now that second tire has come in. So the first tire has already entered, and while it was in there and going at a lower velocity, the upper one had a higher velocity, so it turned a little bit. Okay, not much, but a little bit, and it turned towards the normal of that surface. Now we're assuming that this is a straight line. It's turning towards the normal, the perpendicular line that we have there. Now what is going to happen when it comes back out on the other side again? Well, as you can see, this one is still a little bit in front of that one. Okay, I lied, the bottom one. I just drew the top one a little bit. This one is still a little bit in front of that one because it's still not going perpendicular. If it was hitting this thing perpendicularly, there would have been no refraction. Both would have hit at the same time. Okay, but you can see it's still at a little angle, so this bottom tire is still going to reach the other side first before the top tough tire. So it's going to come out first. And when it comes out, it's going to be again on the tarry surface, so it's going to go faster than the top tire, so then it's going to be bending again, okay, this time away from the normal surface. Okay, so now we have this type of picture, and there it bends a little bit that way. Okay, I wonder if that makes sense to you. Okay, but do you notice how it bends away from the normal? Okay, so when we go from a high velocity to a lower velocity in a medium that causes a lower velocity, we bend towards the normal, and if we go back to a higher velocity, we are bending away from the normal. Okay, that's the first part. That is why when white light enters a denser medium, when it hits at an angle, it is therefore refracted towards the normal of the surface, which would be somewhere there. Okay, and then when it comes back out, it is refracted away from the normal. Okay, so there's the normal to the surface. Okay, it's refracted away from it. Okay, and therefore it looks like it's bending twice. There it bends a little bit off of its original path, which would have been there. Okay, it bends a little bit and then bends a little bit more off of its original path that would have been there. It refracts twice, and that's why a triangular prism works better to not diffract it, to refract it twice. Now the next question is, well, why does it separate the different frequencies or wavelengths? Okay, well, think of it now this time like this. So we still have we're still using tires as our example. Imagine here we have a small tire and we have a larger tire, or wheel, sorry, I shouldn't talk about tires, wheels, and they're approaching also a puddle, and they're going at the same velocity. Both of them are going at the velocity of the speed of light, let's say that. Both of them are going at the speed of light, hitting that. Now, which one has a higher frequency? Okay, hopefully you know that the smaller tire will have, or smaller wheel will have, a much higher frequency than the larger wheel, because if it has to keep up, one turn for this wheel displaces, let's say, a meter, while one turn of this only displaces 10 centimeters. So it has to turn much faster, so the frequency, the turns per second or per minute, is much higher. So when it hits the puddle of water, which one is affected more? Well, I hope it makes sense to you that the smaller one, the one with the higher frequency, is affected more than the one with the lower frequency. So if I look at this, which has the higher frequency of light? Well, let's go and have a look at our don't have it up here, I have it up here somewhere. Let's go look for it. Okay, the longer the wavelength, the shorter the frequency. Okay, we see that from here. Frequency is equal to velocity divided by wavelength. So when wavelength increases, the numerator increases, the frequency decreases. So the longest wavelengths are the red, okay, which means they have the shortest frequency. The frequency for red is lower than the frequency for blue. So the red wavelengths, yes, they will bend, okay, but the red wavelengths will not bend as much as the blue wavelengths will bend. So if we have blue wavelengths, the blue wavelengths will bend more than the red wavelengths, and the other wavelengths in between will obviously bend in between there. So because the frequency for blue is higher, blue is almost like this small tire that is more affected by the change in velocity than the bigger tire, which I should have drawn red and this one blue, shouldn't I? I should have thought ahead on that one. I'm sorry I didn't, but I hope I explained to you why does the blue get affected by the refraction more, or is refracted at a greater angle than the red. Okay, see you in the next videos. Hopefully we're getting to some practical examples soon. Bye.
Was designed for personal enjoyment and education.
QuantumLaserPointers.com.
Okay, so in this video we're looking at the dispersion of white light, and this follows on top of what I said in the previous video, that white light, then we actually perceive a rainbow of colors as illustrated here in this picture. Okay, so what I'm going to do is just explain to you, why is light doing this? Why, when I shine light at an angle into a triangular prism, does it break up into these different wavelengths, and when it comes out it breaks up
Quantum Laser Pointers brings you the infamous double slit experiment right in the palm of your hand. Variations of this experiment spurred public debates between Albert Einstein and Niels Bohr on the true nature of reality. It's been called the granddaddy of all quantum weirdness. This convenient and affordable double slit laser
actually consists of all of the colors viewed at the same time, or at least 3 of the color wavelengths that is being perceived at the same time. But if we disperse white light, in other words break it up into the different color spectrums or the different wavelengths, disperses even more, and eventually to show the color spectrum when it is shone on a canvas or on some sort of light screen. Okay, so why does that happen? Well, the one thing that you need to understand is that when light travels in a vacuum,